All right, you might get asked about what kinds of factors affect the rate of collisions. So, of course, temperature, we've been talking about that we have more particles that can overcome the activation energy at higher temperatures. At concentration, we have more particles that we can collide with, the more particles that are there. But there's also, based on the nature of the reactant, so very large particles tend to react more slowly. So for instance, this is a large biological enzyme or molecule, and let's say that the reaction has to happen here. You know, the likelihood of collisions hitting right in that spot is pretty low. So especially when there's a specific reactive site, and there usually is, large molecules are going to react slow. And it also depends on the physical state. So things, the more surface area you have, so if you had something like a salt, the finer the crystals you're broken up into, the faster it will react, because the particles that are trying to collide with it really only can collide with the particles on the outside. They're not colliding in here. So that's a surface area effect, which makes solids react very slowly, and things that are in aqueous solution or in solution in general are going to react faster because they are mobile, able to make collisions. And of course, the presence of a catalyst. So which one of the following statements is false concerning collision theory of chemical kinetics? And I thought this question was worthwhile to review because this kind of tells you the kind of statements that are true that you want to be making. So molecules collide in order to react. As the concentration increases, the number of collisions per second increases, therefore the reaction increases. And that is true, okay? That's not the false statement. So as concentration increases, you get more collisions, and that's going to increase your rate. All right, B says every collision between the correct molecules will result in a reaction. And the answer, that will be the answer to the question, because that is false. In the so even if they're the correct molecules, they have to have the right orientation. There's two things you always want to talk about: the correct orientation for collisions and sufficient energy. And this does not mention either of those. You cannot have a reaction without those things. See, as temperature increases, the reaction rate increases. We know that to be true. This is because more molecules have enough kinetic energy to overcome activation energy. These are the words you want to use. Try to ingrain them in your brain. This is because more molecules have enough energy, and it's actually, you'd really impress the readers if, along with this, you drew a Maxwell-Boltzmann distribution and showed a line for activation energy and the increased number of particles. Okay. Part D, in comparing two first-order reactions with different activation energies but the same initial concentration, the reaction with the greater activation energy will have a slower rate of reaction. That is absolutely true. So if I have a reaction with an activation energy here and another with an activation energy here, right? This reaction is going to be, the one with this activation energy is going to be faster because it's got more molecules that can overcome the activation energy barrier. Okay, so let's take a look at this question. Consider the following diagram and select the true statement. Variable X represents activation energy and can be positive or negative. Okay, so it cannot be negative. Activation energy is always a positive value. It's always greater than 0. I can't have a negative energy to get the particles or the reaction started. Variable Y represents activation energy. No, no, no. This, of course, you know what this is. This is delta H. Okay. The variable X represents activation, and energy is always positive, and that is the true one. All right, so let's take a look at reaction mechanisms. Hopefully this will come back. A chemical equation does not give us a good picture of how the atoms rearrange themselves to form products. The reaction is the overall sum of everything that's going on. So we need to, reaction mechanisms try to pose what possible elementary steps are, a series of simple what's colliding with what in what order to give us the final products. Okay, so the reaction mechanism is the sequence of those elementary steps. So let's just take a look at an example. So here we have a proposed mechanism. It's got two steps, step 1 and step 2. So the overall equation, this is kind of like Hess's law. I can eliminate things that are on both sides, right? So my overall equation is 2NO, right? NO plus NO plus O2 give me 2NO2, okay? And NO2 is produced in the first step, consumed in the second step, so that's what we call an intermediate. And those are the words you want to use when you get asked what is the intermediate in this mechanism. Anything that's produced in the first step and consumed in a subsequent step, or not there in the beginning and not there in the end, that is an intermediate. When we look at mechanisms, elementary steps, they can be unimolecular, which means only one molecule is reacting. So what that means is you have a particle in there and it's just smacking against the wall, causing the bond to break. Bimolecular reaction involves the collision of two particles. Termolecular involves a collision, simultaneous collision of three particles. That is unlikely to happen. They are rare, okay? It's much more likely that two particles will collide than I'm going to have a three-way collision. All right, so let's take a look at this. In the mechanism, what type of elementary steps does it have? So this one has two particles. It's the same stuff, but it's bimolecular. And this has one particle, two particles. This is also bi. They are both bi. Okay, so a proposed mechanism has to satisfy three requirements. One is the sum of the elementary steps must give the overall balanced reaction. The steps must be reasonable. Termoleculars are not reasonable in most cases because they're so rare. And the rate law for the slowest step must agree with the experimentally determined rate law. And remember, that reminds me, in kinetics, when you're asked how rate constants or rate laws are developed, it is always experimentally. And this question actually gets asked a lot. How do people come up with the rate laws? How do people come up with the order for the reaction? It is done experimentally. I run experiments to figure it out. Okay. So the rate law of an elementary step can be determined by using the concentration, the coefficients of the reaction. So if this is an elementary step and I just have one reactant, I can, and this is a 1, I can make this a 1. That's what we're saying. If I have A plus B, I can write this is just for the elementary step. This is not for the overall equation. Because with an elementary step, I know what is colliding with what, not the overall equation. Remember, I cautioned you, it's not, the exponents are not the balanced, don't come from the coefficients of the balanced equation. But in the case of elementary steps, they do. So, because this is one of these and one of these, this is 1 and 1. This is A plus A, so that's 2A, so I can make this A squared. So this is just elementary steps, okay? So this is not true for the overall equation, only for the elementary steps. So how do you determine the orders of an overall reaction? Answer is experimentally. Okay, so let's take a look at this. Does the following proposed mechanism meet the conditions of requirement 1? Okay, so let's see if the reaction, if this adds up to the balanced equation. The first thing I want to look for is, do I have any intermediates? So I have a OH, OH, and 2 OHs here. Do I have anything else here? I have an HO2 and an HO2. So if I add these together, I get 2H2O2, 2 hydrogen peroxide. My only reactant gives me 2H2O plus O2. And that matches that. So yes, it meets it. State the molecularity of each step. Okay, so the molecularity here, I have one reactant, just one particle, so that's unimolecular. I had two reactants here, so that's bi. And I have two reactants here, so this is also by. Okay. Write the rate law for each of the elementary steps. So this rate law here is going to be rate equals K times H2O2 concentration, right? This one is going to be rate is equal to K times H2O2 times hydroxide, right? I get it from my reactants. And this is going to be K times HO2 times OH minus, or it's not an OH minus. And I got to write the word rate here because that's what the readers will expect if they ask you to do it. All right. Experimental evidence can be collected to determine the rate law. Of the experimentally determined rate law was KH2O2. If this is my, my experimentally determined rate law, which step in the mechanism would be rate determining? Okay, so we haven't talked about the slow step. So the overall mechanism has to agree with the slow step. It includes everything up to and including the slow step. So if I look at my elementary steps, okay, if I look at my elementary steps, the rate elementary step that agrees with the overall rate law is this, which means that step 1 is the slow step. Okay? And there's nothing preceding it, so it's just step 1. All right. So the rate determining step is the slowest step. It's the bottleneck. It's the thing that's determining the rate of the overall reaction. So the rate is the step that gives us the rate of the overall reaction. Okay. So let's take a look at this. So it says the rate law for this reaction is determined to be this. Okay. Oops. The following mechanism has been suggested. So let's see if this, what the rate determining step is. So if I look at this, the first step here is consistent with the overall rate. So this is my slow step. Okay. What are the mechanisms, intermediates in this mechanism? Okay, so if I want to know what the intermediates are, I got to look for something that's not there in the beginning, and I produce it in one step, consume it in another. Let's see, do I have anything else? I is on both sides here. Well, HOI is here, HOI is here. So my intermediates are, number 4 is correct, HOI and OH. All right, let's identify intermediates as well as catalyst. Okay, so we haven't talked about catalyst yet. So a catalyst, I is a catalyst. It is there in the beginning, and it is there in the end. That's a catalyst. There in the beginning, there in the end. I minus is a catalyst. Now, I do have an intermediate here. This is my intermediate, okay? And here I have 2 OHs here, and those are OHs. I have HO2, HO2. So those are both intermediates, and it looks like I have no catalyst. All right, hypothetical mechanism. Identify intermediates and catalysts. Okay, so this is going to be, this is a intermediate, and this is going to be a catalyst. Okay, write the overall reaction. So once I eliminate my catalyst and my intermediates, my overall reaction is A plus C gives me AC. And what is the rate law? And the molecularity. Okay, so the rate law is going to be rate is equal to K times the concentration of A times the concentration of B. You can have a catalyst in the rate law. You cannot have an intermediate in the rate law. Okay? Okay, so here's a question that was on a previous exam. Environmental concern is the depletion of ozone in the Earth's atmosphere. Proposed mechanism for the depletion of the ozone is this. Okay, write a balanced equation for the overall reaction. So let's eliminate our intermediates, eliminate our catalyst, and I end up with O3 plus O gives me 2O2. Okay, identify the catalyst. The catalyst is the chlorine because I started with it and ended with it. When it says justify, it's there in the beginning and it is there in the end. Clearly identify the intermediate, ClO, ClO, produced in one step, produced in step 1, consumed in step 2. If the rate law was found to be KO3 times Cl, what is the overall rate of the reaction? So this is going to be 1 plus 1 is 2. What are the appropriate units for K? Okay, so let's think about this. So I have rate is equal to K times O3 Cl. So K is going to be rate over the concentration of O3 and Cl. Rate is always molar per second. This is molar times molar, molar times molar. This cancels out, and I'm left with seconds to the minus 1, m to the minus 1. All right, what is the rate determining step of the reaction? So because this overall reaction rate law is consistent with this, with step 1, step 1 must be the slow step. Okay. Okay, a couple things about reaction mechanisms to just clarify. They're determined by experiment and must agree with the experimentally determined rate law. The slowest step determines the rate of the reaction. The rate of the overall reaction is limited by and is exactly equal to the combined steps up to and including. So if I have a fast step and a slow step and 3 fast steps, these are what determines my overall rate. Okay? An intermediate is produced in one step, consumed in another. Catalyst goes in as a reactant and comes out unharmed as a product. Does not show up in the final overall equation. So a catalyst is simply a substance that increases the rate of a chemical reaction without being consumed. So here's a reaction where I start with a very high activation energy. I add a catalyst, and all it does is it lowers the energy of activation. It does not do anything to the enthalpy. Okay? There are both heterogeneous and homogeneous catalysts, and they're just defined by the state of matter of the catalyst. So if they're in the same phase, if they're both, let's say, aqueous, then they are homogeneous. Okay? So heterogeneous are more common. I have maybe a solid catalyst and I'm passing a gas over it. Different states of matter, that would be heterogeneous. Okay. Enzymes are simply catalysts for biological systems. They are often very large and very complex, and everything that applies to catalysts applies to enzymes. This is an enzyme, large, complex. All right, so let's label the reactants and products for the forward reaction. Reactants and products. Reactants and products. A catalyst lowers the activation energy but does not change delta H. So use a dotted line to show the catalyzed pathway. And as you can see, it affects the forward reaction activation energy of the forward reaction, and it also affects the activation energy of the reverse reaction. Here's just a simulation of what happens at a heterogeneous catalyst. So let's say I have a solid catalyst, like in a catalytic converter. It adsorbs the molecule and allows for the collision to take place, and then when the product is formed, it leaves. You got to be able to do this. You got to be able to do this. Okay, so if this is reactants and this is product, this is going to be my delta H of my forward reaction, and this would be the delta H of the reverse, right? So this is going to be positive because it's endothermic. This would be negative because it's exothermic. This is my energy of activation of my forward reaction. This is my energy of activation for the forward catalyzed. Okay, this is going to be my activation. So this total line is my energy of activation for the reverse. This is going to be my catalyzed energy of activation for my reverse. This is going to be my activated complex. Okay, the stuff I have in my container once I've made it over the hump and before I start to make products. All right, we're going to stop right there.